Hello everyone, as you know I am Paul, your e-hobby guy, and today's video is going to be about relays. We are going to ask ourselves what relays are, why do we use them, when do we use them, and how to identify them. We're going to look at a couple of different applications and a few different types of relays so that we have a full understanding of what relays are and when we can use them in our projects. So let's jump right in. Okay, as we look at the first question, which is what is a relay? A relay is nothing more than a switch. Now it's a special kind of switch. Here's the symbol for a basic normally open switch. A relay is a switch that is actuated electrically. And so the most common type of relay that we refer to is a relay that has an iron core attached to the pole. So this is referred to in a relay as a pole, and this is referred to as the throw. So if we attach a rod to the pole and we put a coil on this, if we apply a voltage to the coil, a magnetic field is generated and pulls on the rod to close if it's normally opened, or to open if it's normally closed. Now we could have both normally open and normally closed. So if this was a relay, this would be the normally closed, this would be the common, and this would be the normally opened. And so if we energize the coil, the pole moves from one throw to the other throw. And so in the de-energized state, we're going to have a common tied into a normally closed, and the normally open is going to be there floating in space. So if we energize the coil, we're going to move the pole from this throw to this throw, creating contact from the common to the normally open when it's active. Now in many cases there can be more than one common, normally open, and normally closed. So I'll draw some in parallel here. So what I'm showing you here is a single coil here, if energized, will pull three independent poles, and all three of them, separated, completely isolated from each other, will move their pole from one throw to the other throw, from the normally closed to the normally open. Nothing happens to the common in all three cases. This is referred to as triple pole double throw relay, and it's written like this. You could also have a four pole double throw. So the most common are single pole double throw, which would be just one common, normally open, normally closed. You can have a double pole double throw, which would be two of these arrangements activated by the same coil. Triple pole double throw, or a quadruple, but the 3 and the 4 are actually commonly referred to as 3PDT and 4PDT for a 4-pole double throw, because for some reason the industry developed not wanting to put triple and quadruple in there. So these are the symbols used for 1, 2, 3, and 4 sets of throws, of poles and throws for a single relay. And so why do we use relays? What's the purpose? Well, there's two things that you get by using a relay. The first thing is electrical isolation. Now what I mean by that is we have the coil that we're going to apply a voltage to. There's an iron core that's attached to our pole, remember. This coil does not touch this iron core. And so a magnetic field is what causes the pull on the pole and closes the switch. And so there's an isolation between the input voltage and the voltage that is attached to the contacts that we're controlling. So isolation is one of the main reasons that we use relays. And now for the second reason. all switches have ratings. And so let's say I have a normally open switch here, and it is rated for 0.5 amps. And the maximum current that can flow through here is 0.5 amps. Now what if I want to control something or turn on something like a motor that is pumping water in my pool? Well, my motor might take 6 amps at steady state. I can't use this switch. And so we can introduce a relay whereby we apply 5 volts DC, and it only takes 50 milliamps. The contacts on relays are almost always rated much higher. They could be rated at 10 amps, 120 volts AC. And so we can have current and voltage ratings maximums for relays. And so with a very small switch, if I want to activate a relay with a very tiny switch, I can turn on much bigger equipment by using a very, very small switch. And we could take it a step further. So let's say I want to open a bridge, and the bridge takes 1000 amps. Well, we could have this relay activate another much larger relay that's rated for 1000 amps. And so with one tiny switch that's rated 50 milliamps or higher, we can open a huge bridge that draws 1000 amps, 280 volts AC, something with a very much higher rating. And so this is the second reason that we would use a relay. So the first one is isolation. If there's any spikes in electricity or anything happening at the contact level, it can't be passed to the control electronics. And the second reason is with a very small current, very small contact, we can control much larger devices and handle much higher currents. And so in many cases where it's convenient, we will introduce a relay to control something that requires a much higher current than is being supplied by the control electronics at the control electronics level. There is one thing I want to talk about before we jump into looking at actual relays, and that is the different forms of relays. And now I'm not talking about the mechanical form, but there is something that is called a Form A, Form B, Form C, and Form D. A Form A is a relay that has a switch that is normally opened, similar to the one that we started out with. And when actuated, it would close. Form B has a switch that is normally closed, and when it is energized, the switch opens. Form C we also talked about. It has both a normally closed and a normally open contact. And Form D is not very common, but it's out there, is similar to a Form C, where it has a common, a normally closed, and a normally open. When it's energized, it's called a make before you break. It makes contact with the normally open first, and then it breaks contact with the normally closed. So this is shown in the energized state. Normally closed is now open, and the normally open is closed. So just to state again, Form D is a make before you break. And an application that would just jump to mind offhand would be a backup generator. If you lose incoming electricity to your house and you don't want to experience any interruption in your power, which would be typical in something like, let's say, a hospital, you would want a transfer switch that makes contact with the backup generator before it breaks contact with the incoming power. And you would do this with some sort of stored energy that allows you enough energy to make the transition for the switch, for the relay. And so, Form A, it's a normally open, closes when it's energized. Form B is a normally closed that opens when it's energized. A Form C has both a normally closed and a normally open, and a common, of course. And a Form D is a make before you break situation where the common makes contact with the normally open first before it breaks contact with the normally closed. I just wanted that to be clear before we move forward and look at different types of relays. Okay, so let's take a look at some different types of relays here. It's a Form A PCB mount relay. Here's another PCB mount relay. And you can see this is a double pole, double throw. It may not be too clear in your picture, but you can see these two terminals at this end are separated from these three. And this is just kind of helpful information, but most likely this is the coil. And a good quick way to test would be put a meter on these two terminals. And if you get a reading for the coil resistance, you'll know that it's the coil. But the first stop you should make when using a relay is to look at the model number and get the data sheet as always, and it'll tell you which one's common, which one's normally open, and which one's normally closed. And so this looks like it's a Form C double pole double throw PCB mount relay. Here, let's look at another one. This is a much larger relay. The contacts on this you can tell by its sheer size. You can see the pole here, the normally closed and the normally open. These contacts are rated at 10 amps at 240 volts AC. This is a 4-pole double throw relay. And so the coils can be activated using many different voltages. We can go to very low voltages in DC, up to very high voltages in DC, and the same goes for AC, depending on the application that you're designing, that you're using. In this particular case, and let me just grab another one that's very similar to this. This nice big honking guy right here. It comes with a base, and it shows you which one is normally open, which one's common, and which one's normally closed. Many of these larger relays come with an LED to show when it is active. And so, just looking really quickly at this base, this is actually a DIN mount base, which a DIN rail is a rail that is like a channel that you would hook and snap onto, and you could mount a rack of them side by side. Another type that is often used is the one that comes, it's really referred to as a module type. This is kind of a more versatile one where it's got two voltages, a 6 volt and a 12 volt, and you can select which voltage you want with this switch. So you can see here it's a common, normally open, normally closed. Common, normally open, normally closed. So this is a double pole, double throw. Positive here, negative here. The resistors are just creating the voltage divider for the 6 volt, 12 volt selection. And the red LED comes on when this relay becomes active. Here's another very similar one. It's a module type. Here's another relay that is a 4-pole double throw. These are the two power. Very simple. It's just another continuation. This of course has a base. Here's another very big. This is a 120 volt relay. The contacts are rated up to 15 amps, 277 volts AC. And looking back really quickly, anything, as we know, that is a common, normally open and normally closed, is a Form C relay. This one you can see into pretty clearly. Once again, is a common, normally open, normally closed, which means it's a Form C, double pole, double throw. And this is the coil. Another thing, you can just physically see that coming down from the coil will be the contacts that are used to energize the coil. Again, here's some PCB mounts that I had lying around. These are very typical double pole, double throw Form C relays. Very common PCB mount. These take very low current to actuate. I do have solid state relays here, a little sleeve of them, and these are semiconductor based, not using a coil. And two of these, I would have to look at the spec sheet definitely for this, but two of these are what would be considered the coil, though it's not, but they're the activation contacts, and two I believe this one's normally open, so it's a Form A relay, solid state. So this is a Form A solid state relay. It only takes 8 to 10 milliamps to activate this, which is very good. Now I did want to just look at some boards that I'm going to scavenge. I had them lying around, didn't get around to scavenging, but now that we know what relays look like, you can see right away this is the relay. I would have to desolder just 5 contacts there and I'd be able to pop this guy off. Here's another one that I still haven't scavenged, but there you go. It's got a green sticker, but that's a relay. It's another board I'm going to scavenge off of, but here we can see two relays. Here is one last module that I had lying around. I haven't gotten to use it yet, but it's a 16 relay module that can be used with microprocessors to, fully automate other, as we know, other higher voltage devices. And so with a microcontroller, you can set schedules and control appliances, lighting, anything you can imagine that's a higher voltage, and hook them right up here to each one is Form C, common, normally closed and normally open for all 16. You can get these in different numbers of relays. In other words, it comes with a single relay, 2, 4, 8, 12, 16. I mean, 16 I think is probably the highest I've seen, but there may be more. So I wanted you to be aware that depending on what your needs or your project, you can get them pre-mounted and programmed through a microcontroller. We'll go to the breadboard. I'll wire up a relay really quickly. I'll show you the coil voltage and we'll light some LEDs or do something to show you that the relay is working the way we described, just to show you one working in practice. So here we have a Form C relay hooked up in this schematic, and so in the normal state, through the normally closed, we have this green LED is getting the 5 volts through it. This is current limiting resistor for this. This is a current limiting resistor for this. This button provides 5 volts to the coils. And so, in its non-energized state, the green LED is lit. When I energize it, the pole switches over to the other throw and provides power to the other LED. And while it's passing through space from the normally closed to the normally open, neither of the LEDs are lit. But that's a very short period of time because they're very close to each other. And so this is just a simple example of a Form C relay wired and being used in a way that switches the power from one source to another when energizing the relay. Okay, so I rewired this circuit just to use a transistor as a switch that's going to activate the relay, which is often done. And so I'm going to use this resistor on the gate to trigger. This resistor is tied into the positive 5 volt rail. The collector is the top pin right here. The middle pin is the gate. The bottom pin is the emitter. And so I'm going to trigger it using this resistor on the gate, and you can see it acts just as it would when I was using a regular push button. And so this transistor is being used as a switch. But my whole point for doing this is actually this is a diode. And so when you're using sensitive electronics like a transistor, when the relay is de-energized, the core passes down through the coil again, but it acts in reverse. It induces a voltage spike in the coil which gets sent back and can destroy a transistor like this. And so it may work one time and then you may find that it doesn't work anymore. And that is because on the de-energized cycle, the core moves back down through the coil, inducing a high voltage spike, destroying the transistor. And so to prevent damage, we put in a diode across the coil such that it prevents the voltage, the current, any current from flowing back and destroying any sensitive electronics that are on the trigger side of the coil. And so we can safely use this as a trigger mechanism which can be triggered by any other means. I'm just physically putting it here, but you could have a microcontroller. Anything that's sensitive will now safely trigger the transistor without worry about feedback from any voltage spikes that are getting passed back during the de-energized cycle. So just thought it was worth mentioning, and so let's move on. And so everybody, that's it for today's video. Remember to like, share, and subscribe if you liked it. I hope you learned something. Again, thank you for taking the time to watch, and I'll see you next time.